Okay, so the first talk of the session will be Teaching Programming with Graphics, Pitfalls, and Solutions by Luca Chiodini.
Thanks for the introduction. Hi, everyone. I'm Luca, and I'm about to present Teaching Programming with Graphics, Pitfalls, and a Solution. Now, bootstrapping every talk is always a difficult part. Let's see if I can get your help in this. Here's a claim for you to assess. Maybe you or one of your colleagues are using exercises with graphics, say, as opposed to just exercises with numbers or strings when teaching an introductory programming course. What are some quick pros and cons you can identify about that? Sure.
Be more interesting for a student?
More interesting. Others?
Requires geometrical, mathematical background.
Oh, requires some complicated background that not everybody might have. Other claims? This seems mostly like it. I think I had an easy time guessing you. On one hand, some people describe this, oh, this is like fun, it's attractive, it's more motivating for students. And on the other hand, some people say, well, but it's a little bit too hard, maybe it's too complicated, or maybe it's even distracting from the main purpose. I'm teaching kind of introductory programming. I don't want to teach like geometrical concepts. So it seems that we have like two teams here. One is a little bit about the complexity, and one is about the engagement. And then a lot of people, when they teach like an introductory programming course, especially if it's like in high school, they say, well, I don't really want people to become programmers, as we have been just discussing, but maybe I want to teach like some computational thinking skills, whatever that means exactly. But one of the skills that is often cited in computational thinking is like, oh, I want them to be able to do problem decomposition. I want them to identify subproblems and solve them. So we have three teams. And so when we teach introductory programming with graphics, we would like to have like these three goals associated with these three teams. One is that we have complexity and we would like to manage this complexity. Another one is that we have engagement and we want to have, sure, students engaged, but we want to direct this engagement towards meaningful concepts. We want them to learn programming in the end. And then when it's about problem decomposition, we would like to have a library, an approach that allows us to have like a clean problem decomposition. So we have these three goals: manageable complexity, meaningful engagement, and clean problem decomposition. Now the first part of this talk is about identifying some pitfalls that we identified in existing libraries to do programming with graphics that have to do with these goals and that they might hinder the reach of these goals. And to show you those, I'm going to use a basic example. This house, this is a very famous example, using some existing libraries. But before showing the code, I want to make an important premise. This is about teaching complete novices, and it's about teaching them programming. So the actual goal in the end is to have like some basic essential programming concepts. Now here's the first snippet of code. I'm going to use Python, very popular language nowadays for introductory programming, and one of the many libraries, this one is called CS1 Graphics, that is supposed to be used to teach introductory programming using graphics. So here is how it would go to create that house I just showed you. We would first create an empty canvas, then we would create, say, a square for the floor, then we position the floor appropriately at certain coordinates, we add the floor to the paper, and then we need to do the same for the roof. We don't have a function directly to create the triangle, but we can create a generic polygon, and we can specify the points of the vertices of this polygon. And we have our roof. We can add the roof to the paper, and this is how the code looks like. Now, if you think at introducing this piece of code to complete beginners, you might think that you would have some difficulty here in explaining what are all the language features that are used in this code. Well, sure, we have like some functions that we need to use, but this goes beyond functions. Here we have like object instantiation, and then we not only have functions, but we have objects, so we have method invocations. And then we even have like a variadic constructor here for polygon that can take in a variable number of parameters. So we have like a lot of language features, and this is the first pitfalls that many libraries incur into. Now, for something different, let's say that we want to create a second floor for our house. This is how we might extend the code. This is the same code as before, and I'm just going to add these 3 lines at the end. I'm going to create the second floor, I'm going to position it appropriately, and I'm going to add it to the canvas. Now, very quick show of hands. Who believes the actual result of this code is the one on the left? 1, 2. Who believes it's the one on the right? A couple. A lot of shy people. That's fine. So the surprising thing, or maybe not so surprising, is that it's the actual result is the one on the left. Because what's going on here is that against the fairly typical novice intuition, this is not creating another floor object, but it's merely creating 2 variables that refer to the same object. And so here we have mutation going on, and this is actually quite complicated to introduce novice programmers to. And so mutability is this second pitfall that we identified that might hinder reaching the goal of manageable complexity. Now, onto the meaningful engagement. So here we have the student who's unable to create or struggles to create the desired house. Now, here is what might happen. The student goes into the documentation of the library, looks a little bit at what's available, and then they discover that there is actually a class that's called image that takes in a file name. Oh, that's an amazing discovery for the student. This is what's going to happen. The student is going to go on Google, it's going to type house, it's going to look a little bit, maybe this one, maybe not exactly, let's see. Okay, this one looks great. This is a great house. I'm just going to save this one on my desktop, and then I'm going to solve my problem just by creating an empty canvas and adding it the desired image. And here we have it, our amazing house. And that looks much better than the ones I had just programmed before. So even though external images have their purpose in introductory programming, actually they might hinder the engagement. And this is why we're considering the ability to load external images a pitfall. For something different, here is how we might solve the house problem using Pirate and its image library. We might be able to create the floor using the square function. We might be able to create the roof using the triangle function. And finally, we can combine them together to create our house. Now, this code is very nice, gets to the point, very terse. Now, why exactly is it that we are able to solve our problem so tersely? Well, the reason is the Pirate API, the library, the image library of Pirate, actually has a large number of primitives. These are kind of all the possible shapes that one can create directly, and they are all one function call away. And then we have like a large way to compose this, a large number of functions that are able to compose these images. And so what happens is that students, instead of actually defining their own abstraction, say the one that creates an equilateral triangle, can just spend time into looking into the documentation and find the right function. And that distracts a little bit from the goal, that is teaching programming concepts and not teaching a specific library that maybe they're not going to use again after this introductory programming course. So having a rich API is the second one of our pitfalls that go under the meaningful engagement goal. Finally, let's get to this third, a little bit more weird goal, perhaps. We would like to have like this clean problem decomposition. Consider this house and consider a simple variation of this house. The previous one had like the roof at height 87. This one has the roof at height 120. This is the same code as before. Could you help me in changing this code so that we get to the right picture? What do I need to change? Some help? Yeah, there were like 287. Maybe this is not the best code, but this is how it was written. We need to change this 287 to 120. Is that it? Oh, I need to change the move somewhere. There is a move there to 137 for the y coordinate that needs to be turned into 170, which is a little bit of a weird number, which results like from 50, the center of the square, plus 120. And this is really weird. I mean, besides that this code is maybe not exactly how you would have written it in the first place, this is not how we would like this, this problem to be solved. I mean, we only wanted to change our roof. This is a more general description of this. We have our problem, we need to draw the house, and we divided our problem into two sub-problems, drawing the floor and drawing the roof. And then we came up with solutions, with programs for those two sub-problems, the floor and the roof. And finally, we were able to combine the solution into a house. And so we have like these two sub-problems. And the key here is that we would like to solve them independently. But what happens in the previous code is that the floor, the position of the floor depends on the canvas origin. The coordinates at which it's positioned, those are global coordinates. And the same goes for the roof. It depends on the same canvas origin. And so here we have like two sub-problems that depend on a shared global value. And that's why global coordinates are considered a pitfall to achieve clean problem decomposition. Now, this problem was recognized a very long time ago already from Papert when they introduced turtle geometry. Because turtle geometry, if you think a little bit about it, provides a local perspective on drawing. You're embodying the turtle, and then you're instructing the turtle for certain commands. And so you have here your house. Now, the original implementation for Turtle was in Logo, but nowadays Turtle is available in almost any programming language. There is a library. So I'm still going to use Python for clarity. And I'm just going to solve the first sub-problem here. We need to create the yellow square. I'm going to change the pen color of the turtle. Here for brevity, I'm just going to do the outline. And then I'm going to use some repetition construct, and I'm going to move the turtle forward, and then I'm going to turn it right by 90 degrees. And by following exactly what the Logo manual does, I'm going to package this piece of code into a function or a procedure, if you wish. And then imagine that we have solved the roof problem in the same way. So we have two functions, one that draws the floor and one that draws the roof. And then I'm going to call these two functions to be able to draw the house. But this is what's going to happen. The turtle is going to draw first the square, and then it's not turning in the right way, and it's going to draw the roof not in the way we want. And so what happens here is that we need to have some glue code here. We need to have an instruction such as turn left by 60 degrees to adjust this code and make it produce the image we want. And what's the interesting fact here? Well, solving the floor problem actually depends on and even changes, mutates the turtle's state. And similarly, solving the roof sub-problem depends on and changes the turtle's state. And that's why we can't have this clean problem decomposition. And so here is our second pitfall, the turtle state. Now, this problem, again, was recognized long before. This is, I think, goes back all the way to Henderson, 1982. He introduced functional geometry, and it's kind of this approach that is more taken into the functional programming community to treat like images as values. And it's also the approach that it's embodied in the image library for Pirate. And so there we only have like combinators, and there is no notion of a global coordinate system. We only have a local coordinate system, which students discover when they look at all the combinators I was showing you before, and they discover that there is one, or actually many, but one specifically, like put image, that, okay, takes two parameters, an image and a background, and places the image on the background so that its center is located at a certain coordinate with respect to the bottom left of the background. And this is good for solving certain kinds of problems, but it's easily abused by students and also by some teachers when they teach in Pirate. This is an example that comes from the Bootstrap hour of code. This is the final task of the hour of code, and this is what the student is being told to do. Look, your task as a programmer is to change the coordinates of these subproblems, and maybe if you want, add a little bit more. But the problem here is that every subproblem, sure, there is no global coordinate system, but there is a local one, and we are abusing the local one as a global one, because every subproblem now depends on the background's origin. And that's why, even though they are useful for certain graphics, local coordinates can also hinder clean problem decomposition. So that's about the pitfalls. Now, what do we do as a solution? Well, the solution is very easy. On one hand, you just don't do any of this. What's the problem is now what you can still do. And so the rest of my talk is convincing that you can still do something meaningful even without doing any of that. And we embodied this approach in a Python library that we are dubbing Pytamero. And here is how solving the house problem would look like in Python using Pytamero. Now, unlike the previous snippets, this is a complete Python program, meaning it's complete with imports and output. So this is, in full honesty, what you need to do to program with Pytamero. You need to import certain names from the library, then you create the floor, very similarly to how you're doing it in Pirate. You create the roof. Notice that here you don't have an equilateral triangle function because the API is very slim. It doesn't offer you a specific equilateral triangle function. There is only a generic triangle, and students then can define their own abstractions once they have seen repeated code over and over. And you can still combine the two subproblems using a combinator, and finally you can show the house. And this is everything that the students need to know in order to being able to create a house with Pytamero. Now, our approach pushes and encourages to decompose a problem visually. Here's what I mean by that. This is an example taking the emblem of the International Red Cross. We see naturally that we have a red cross onto a white field. And then we also see that the red cross is made by a horizontal arm and a vertical arm. And if we want, we can even say that the vertical arm is an horizontal arm rotated by 90 degrees. And so this is actually fairly easy. Now, it might be even too easy, and you should be complaining, okay, that was a trivial example, that's not fair. What about more challenging graphics? So now I'm just going to take it a little bit one step further by showing you this heart. How we can program this heart? Well, first of all, it might look easier if we rotate this heart by 45 degrees. And now, what are we going to do? We're going to use, again, some Pytamero primitives. Here, we can combine them and rotate using everything we have seen so far. And now we need to introduce a new concept that every graphic has a pinhole, a designated position for pinning, that is then used to combine this graphic with other graphics. And so what's actually happening is that these graphics have a pinning position. There is a function in Pytamero to repin a certain graphic into a different location, and we control the locations in which it's possible to pin. And we can then use the generic compose function to compose the two graphics, aligning their pinning position. And finally, we rotate the heart to achieve our problem. The neat thing is that by leveraging this composition pattern over and over and over, students can actually create stuff that is relevant and they like a lot. Pac-Man maze is a common example. Games are often very popular. And here they can create like a full-blown maze just by composing the specific tiles. This is very common to tile-based words. And the specific tiles, in turn, are composed out of Pytamero primitives. We can actually create meaningful graphics as well, not necessarily just games. One of them is warming stripe visualization. That's actually something interesting. Or if you're doing, let's say, a science class, you might be interested in having your students, instead of just looking at a periodic table of elements, create their own periodic table of elements. Or say you might want to use a graphic that is culturally relevant somehow. Here is, for example, the Swiss railway clock. This is culturally relevant for Swiss, but it's also somehow known worldwide. And there are actually many more examples. a touch or a point that touches upon something we have been just discussing in the keynote. Pytamero attends to the idea that students, especially younger students, might want to program in their own language, and it attends to this point only at the level at which Pytamero situates, meaning a library. And so we have been fully localizing the API, and that means not only the function names, but also the parameters, the error messages that we give, and the documentation. And here is how the same house example would look, for example, in Italian. It's quite cool. There is more in the paper. We have some more example of how students can create their own data visualization as opposed to just using a library that visualizes the data. Here the idea is, well, why can't you compose the graphics out of primitives? And so you're learning about data visualization, but you're also learning about programming at the same time. There is a discussion on how combinators offer multiple ways to decompose a program by the very nature in which they are written. There are some beautiful connections to algebra that unfortunately I don't have time to explain right now. And there is also a discussion on how we are gradually introducing types, even for Python, which is not like standard practice, and how we are connecting that to the documentation. Now, some limitation, very briefly. I presented some pitfalls at the beginning. It's mandatory for me to say that I understand that different contexts call for different goals, and so not everything I said is applicable to every context. And the second major limitation is that we have so far been using Pytamero in teacher training courses, in a first year university course, and in high schools, but we only have like anecdotal evidence of its of the fact that it's working to counter some of these pitfalls, and we are working on studying its effectiveness with a more rigorous evaluation. So I'm inviting you to check you out. We have a platform for this library. On the platform, you obviously find the documentation of the library and how to install. That's just a pip install Pytamero away. But you can actually do something even more interesting. You can program with Pytamero directly in your browser. The website offers more than 150 activities with Pytamero, and there are also some guided curricula that sequence the activities for you. And I'm very happy to report that some of these activities and curricula have been created and are currently used by some Swiss high school teachers. And that's it for what I wanted to say about teaching programming with graphics, some pitfalls and a solution. Thanks.
All right, great talk. So we have 4 minutes, so chat about the talk, and then we'll have a few minutes for questions about after that. Yes. Yeah.
Sorry, just to repeat kind of how we're doing questions in SPLASH-E. So we're going to do small group discussions at tables. So if you're not at a table with a small group, maybe join a small group. So we're going to have those conversations for 4 minutes, and then we'll open up for big group questions. Thanks.
Into a few questions for the speaker, and then as we get towards the end of the question period, we'll have the next speaker set up as well. Okay, so just raise your hand if you have a question. All right, right there.
So I was looking at your pirate example. I think you were a little bit unfair because that's more about function composition than anything else, right?
Okay. What do you mean by function composition?
That you right that code is breaking it down, like you're suggesting, but it's putting it all into one global expression instead of breaking it down nicely inside the code like you do in separate expressions.
Right. I assume you mean this piece of code then. Let's see. Maybe we can get the...
Yes.
You mean this? Oh, but I didn't write this one.
I know.
took this one from Bootstrap, which is the leading curriculum that uses...
Yeah, I understand. But that's basically decomposition, right?
Right.
So...
But I mean, you see that some of these sub-problems might be merged into in a hierarchical structure. I mean, this is about building a snowman. And so you have certain things...
I completely agree with you. This is not the type of code I would encourage, right?
Okay.
But my more important point was about aligning the pinholes. So it seems to me like you didn't talk about place image, which is based on using a coordinate system, which I think beginning students learn in high school. They know what X and Y coordinates are, and I think that might be easier than figuring out how to align the pinholes for them.
No, there is definitely, I mean, I'm not blaming coordinate systems altogether. And I know that there are actually some very great uses for coordinate systems. Say, for example, if you're modeling any kind of like real world game or some kind of graphics that is about like physics simulations maybe or games. And therefore like you have your problem that inherently uses a coordinate system. And then by all means, that's great. You want to position stuff at a certain coordinate because that's where the stuff is supposed to be. And I wouldn't use pinning for that. The problem that we're describing here is that these coordinates, especially very early on, can be abused. And students tend then to write, this is actually from experience, in TAing courses that use HTTP, how to design programs, as an approach, and seeing the students that write in their final projects code that has like numeric constants all over the place, and they haven't really gotten the gist of like composing stuff where more appropriate combinators would be available, and only using coordinates for places where coordinates are really required. Saying I'm modeling something for physics, and I need to place something at a certain position, X and Y.
I agree. Take a look at animated problem solving. It'll take it a step further than how to design programs.
Okay.
Yep.